Right. Okay, so this is the new section we started last week, frequency domain design. We went through a couple of slides, right? But I just want to give you a little summary to help you get back to this mode, frequency domain. Uh, so the first thing to uh, uh, to know about is that every system is actually cascaded sequence of blocks like this, right? G1, G2 up to Gn, right? Uh, so when you operate a control loop, right, signals actually uh, travel from input side to the output side and then also get fed back, right? So you can imagine that the same signal is going, producing an output and coming back and again feeding back. So it's like a loop, right? It's like a loop. So when you feedback signals, you have to do it a bit carefully. It is very important concept in controlling the response, that is YS, to be closely matched with the reference RS, but in the same time you have to do it very carefully, right? Now, then if you look at signals, what is RS? RS can be a time varying signal. Okay, sometimes you give a certain signal and then after a certain while you change the signal to different value. Okay, so if you have a good control loop, the response also will follow the reference very closely. Uh, Now, if you look at the signals again, as you know from Fourier transforms, right? Any signal, right, can be decomposed into a set of sinusoidal frequencies components, right? So, uh, therefore, if you want to represent a signal, you can represent the same signal using its sinusoidal components. Okay. Now think about various signals that you have, triangular signals, trapezoidal signals, step signals, right? Now, all these signals can be broken down to number of sinusoidal waveforms. When you combine them together, you have the what you call trapezoidal or triangular signal. So therefore, it is good and appropriate to analyze a system in terms of how a sinusoidal waveform travels through uh, the system and comes back and fed back here. So that is why we use this frequency analysis. Okay, frequency analysis. For a range of frequencies, if the loop operates properly, it is evidence, it is kind of verification, proof that for any signal, this will operate properly. Okay, so there are an infinite number of the signals, right? All possible signals for a plant like this, right? There's no way for you to put every possible signal and check whether still the response is acceptable. So that is not very rational, not very logical. So that is why we do this frequency analysis. So when you say frequencies, right, any signal is actually composition of sinusoidal frequencies. So we look at how the loop operates for various frequencies. And then if the operation or the response within the frequency range of interest is okay, is satisfied, then we are happy, right? And we conclude that, okay, fine. Now this is loop is ready, it is good enough, it will do the job. And of course, um, We are concerned on within a certain bandwidth, that is frequencies from 0 to some frequency, right? We are not really interested in very, very high frequencies unless for a very specific case. Otherwise, it will be a limited frequency range. All of the signals that we talk about are actually limited to a certain bandwidth. So if those frequencies within that bandwidth can travel from here to here, right, in a satisfactory way, then we are happy. So that is the story behind this discussion, right? So we say that when a signal passes from here to here, right? Let's take that signal as a sinusoidal waveform, right? Representing all of the sinusoidal waveforms, right? So that waveform, when it passes through the first block, right, undergoes attenuation or amplification and also phase delay. Sometimes phase advance, but usually most of the time phase delay. So when it goes to the second loop, second block rather, the second block will also introduce an attenuation and also a phase delay. So this process continues and eventually you get an output over here, right? Now what you need to look at is, after going through all these individual blocks, right, what comes out as the response here, Ys, right, it is actually represented by this phasor. So it is attenuated by a factor of m, right, and it is phase delayed by an angle phi. So that is the final outcome, the total effect, the total change uh, uh, of the signal when it passes from one side to the other side uh, of the system. Oh, if this attenuation or amplification is acceptable, and if this phase delay is also acceptable, then there's no problem. Okay. So this is actually very clear now, right? We need to look at this frequency based attenuation and phase delay, and this frequency omega will represent all of the frequencies of interest. Okay, it's not just one single frequency. So some frequencies you have a higher attenuation than the other ones. For some frequencies you have a higher phase delay than the other frequencies, right? So both of these attenuation, that is magnitude gain, and the phase, that is phi, they all frequency dependent. Okay. So like, for example, if you send a signal of, let's say, 1 radians per second through this block, let's say it attenuates by 0.9, the factor of 0.9. Okay. So 10% drop in magnitude. Then you send a 10 radians per second signal, right? It will not attenuate by the same factor, 0.9. It will have a different factor. So that's what you need to understand. M is frequency dependent. Okay. So this is the last thing we did. So if you look at the entire loop, then, right, the forward loop gain from left to right, that is from here to here, right? Total gain is the product of all the individual gains, mij omega, from I equals 1 to n. You have to multiply all the gains. Say first block 0.9, second block 0.8, third block 0.85, whatever it is, to multiply. And it is frequency dependent. Okay. So when you write down the gain, we usually write down in decibel, dB, right? So dB conversion, I'll show you in a little while. So there what you do is you get the dB of individual gains, mi j omega, right? You can add the gains. right? You can add the gains in dB. When you convert it into dB, you have a series of blocks. An individual block has a gain. If it is absolute gain, you have to multiply all these gains. But if you represent the gain in dB, dB is power, so therefore you don't have to multiply, you need to add. You need to add powers together. As you know, when you multiply numbers, right, if you represent the numbers in terms of power, right, 10 to the power something, you just need to add the powers together. Powers, you don't multiply, okay, right. So gain is represented using two methods. One is the absolute gain. The other one is decibel gain. This one. Okay. In decibel gain, you add the individual gains, the block gains. In dB, you add them together, summation. But if you don't use dB, you use absolute gain, then you multiply them together. Okay. Right. And phase, if you get one single block producing phi I j omega, ith block, right? Then you have to add them together to get the total gain. Just like over here, you are adding these phase delays. Okay, right. Please ask if you have any questions up to now. Okay, so let's move forward. I think everything is clear to everyone. Now, what are these blocks? The next discussion is what are these blocks? Again, there can be many possibilities, right? First order blocks, second order blocks, so many different types of combinations. They can be rational polynomials of S, okay, in most generic form. But again, if you look at what are the elementary blocks from which any of these blocks can be created, right? The issue is then uh, to proceed from here, we need to figure out what are these blocks, what are they made of, then the phase and gain of these elementary blocks we need to evaluate. Then only we can make we can proceed from here, right? So that is why we figure out this phase and gain of common blocks or elementary blocks rather. Okay, what are those? You can have a pole or a zero at origin. Sometimes when you deal with transfer functions, you see this one. There's a pole or a zero at origin, right? So that is just S in the numerator or denominator, 1S, right? So if you just have S as a isolated element S, you can say this is S plus 0, right? And when you set this to 0, S plus 0 equals 0, S is 0. So in other words, it's a pole or 0 at the origin. If there's isolated S in the numerator, it is a 0 at origin. And if you see an isolated S in the denominator, it's a pole at origin. Okay. This is one common elementary block. But in addition, you have first order block, 0 or pole. For example, if you have S plus 5 in the numerator, it is a 0, right, at minus 5. If you have S plus 5 in the denominator, it is a pole at S equals minus 5. So that is first order block. But in addition, you can have another elementary block that is a second order block. second order block. That is, remember S square plus 2 zeta omega ns plus omega n square. That kind of second order block. If it is in the numerator, it's a pair of zeros, conjugate, right? Pair of zeros. If you get the second order block in the denominator, it is a conjugate pair of poles. Okay. Now these are the elementary blocks out of which you can build any block, like over here, G1, G2, up to Gn. These blocks can be made of the fundamental or elementary three blocks. Pole O 0 at the origin, first order block, pole O 0, right? And also second order block, pair of poles or pair of zeros. There's nothing more than that. Only three different elementary blocks out of which you can build any transfer function, any block. So therefore, now our discussion is converging from the vast uncertainty to a very clear, finite set of items, right? So now our way forward from here is that to visualize and see and understand what is the gain and phase of a pole O 0 at the origin, and then what is the phase and gain of a first order block, 0 or pole, and then finally what is the phase delay and gain of a second order block, that is pair of conjugate poles or pair of conjugate zeros. So if we understand the phase and gain of these individual blocks, right, we can actually visualize the phase and gain of any other block that is composed of these elementary blocks. Okay, so that is how we organize the way forward from here. So let us take pole 0 at origin, pole O 0 at origin. In one of your blocks, you have a pole at origin or 0 at origin. So in the block, you will identify this as s to the power plus or minus n. What is that? Let's say n equals 1. For the moment, it is just s to the power plus or minus 1. If it is plus 1, it is a 0 at the origin. If it is minus 1, if it is a pole at the origin, because minus 1, power minus 1 means s is in the denominator. It is 1 over s. Okay. So it is basically a block, say a block like this, right? And inside, whether you have s, or it can be a block like this. Inside, you have 1 over s. Oops. So the first one is 0 at the origin. 0 at the origin. This is 0 pole at the origin. Okay. Now we are doing frequency analysis, right? Frequency analysis. So what we do is we take S, right? Remember our pole plane is something like this, right? And this is the real axis, and this is the imaginary axis, right? This is actually j omega axis. This is actually j omega axis. So you figure out some point here, right? J omega. J omega. So when you say S equals j omega, it is the frequency response, pure frequency response. So you pick up this S, right, and set it to j omega. So when omega is 0, you are here. When omega increases, You are following this vertical axis, frequency axis, and you generate a phase and a gain for various frequencies. Okay, that is how we know about the frequency response of the block. So our block is now either S or 1 over S, right? Either this one or this one. Whatever it is, we call it GS, but we substitute S equals J omega because this is pure frequency response, what we want to find out. So it becomes GI, right? That is the block of J omega. Block is actually SO1 over S, and block is represented by S to the power plus or minus N, right? So S equals J omega in this particular case. So it is J omega plus or minus N. Now, when you say gain, right? If you have a gain is actually the magnitude of the vector from here to here. It is vertical vector. So the magnitude is just simply omega. So it is omega plus or minus n. Omega to the power plus or minus n. Okay, so n means the order. You can have 1 0 at the origin, or 2 zeros at the origin, 3 zeros at the origin. Or if it is minus 1, 2, 3, you can have 1 pole at the origin, 2 poles at the origin, 3 poles at the origin, like that. Now this is the magnitude. So if you see a pole at the origin or a zero at the origin, right? And if you send a frequency signal, right, it will undergo this magnitude change because of that pole or zero. That is what it says. Now, if you want to represent or present this magnitude change in terms of dB, this is what you do right below that line, right? You raise this to the power, you take the log of this one to the base 10. So log of omega. When you have plus or minus n, this plus or minus n comes to the front. When you take log, that's what happens, right? Plus or minus n. But this is not just log, but it is 20 log. So at this point, I recommend you refer some notes on decibel representation of the signal amplitudes, right? Signal gains, etc. There are so many documents on the internet. You Google it and you self-learn it. It says it, right? How do we represent magnitudes, gains using decibel? Why this 20? You will find that out, okay? Right. So for the moment, it is basically 20 times log of the magnitude, right? When you express the magnitude, the gain in terms of dB, this dB is the unit here. Then the phase of the block, phase is the angle, and as you can see over here, the angle is 90 degrees, right? If it is a zero, it is positive phase. If it is a pole, it is negative phase. Okay, depending on whether you have S in the numerator or the denominator. Any angle in the coming from the numerator is positive. Any angle coming from the denominator is negative. So therefore, it is plus or minus n times tan inverse omega over 0, which is basically 90 degrees. So if you have two poles, 2 times 90, 3 poles, 3 times 90. Okay, if it is a pole, it is negative angle. If it is zeros, it's positive angle. So the best way to properly understand this phase and magnitude or gain effect of a zero or pole at the origin is to use MATLAB and visualize it. And you can see this little code over here, Bode plots of a 0 and a pole. The first thing I need to do when I use MATLAB is to declare the function I have. So I have s plus or minus n number of zeros at the origin or n number of poles at the origin. So to make it as simple as possible, I take only one pole at the origin and only one pole or 0 at the origin. Because I know if you have more than one, that is 2 or 3 or 5 or any number of poles or zeros, I just simply have to multiply this. Okay. And when it comes to gains, you just have to add phases, you just have to add the phase delays. Okay. For gains, you have to multiply. And again, if you represent gain in dB, you need to add dBs. Okay. So this is what I do. I first declare the function I have using TF command, transfer function command, within bracket, numerator, denominator. So here the numerator is 1, 0. 1, 0 means what? Can anybody tell me? When you use the transfer function command in MATLAB, it has two arguments, first one and the second one. When you have first one 1, 0, what does it mean?
S.
S. It is S. This is S plus 0, right? This is the denominator, 0, 1. 0, 1 means basically 1. You need to have same order here and here. That is why you have the leading 0 here, right? Then you use this command, Bode command, B-O-D-E, Bode. Argument is sys. Sys is the transfer function we already generated. In this particular case, it is a 0 at the origin, right? And it prepares or shows you the Bode plots. I will show you in a moment what is a Bode plot. And right after that, for a pole at the origin, and you can see the transfer function here is different than what we had earlier. Now it is 0, 1 in the numerator and 1, 0 in the denominator. So this 1, 0 comes down over here. The 0, 1 is now up in the numerator. 0, 1 means 1. Denominator is 1, 0. That is s plus 0. That is simply s, this transfer function. Then you draw the Bode plot, Bode sys. Now, when you have two Bode plots on the screen, you need to have them side by side. So therefore, you partition your display using subplot command. Subplot 1, 2, 1 is 1, 2, 2. Right? You have first one row and two columns. 1, 2. And then here you go to the first column. Here you go to the second column. So this is the result. On the left, a 0 at the origin. On the right, pole at the origin. Okay. Bode plot has actually two graphs. First one is the magnitude graph. The other one is the phase graph. Phase graph. So if you have a 0 at the origin, if you look at over here, right, the x-axis is 10 to the 0, which is 1. This is frequency, 1 radians per second. And this is 10 to the 1, which means 10 radians per second. Okay, 1 to 10. And here, from here to here, this is 2, 3, 4, 5, 6, 7, 8, 9, then 10. This calibration is non-linear. This is logarithmic calibration, right? You have the bandwidth of 1 to 10 radians per second. So for all these frequencies, phase is 90 degrees. If you have a 0 at the origin, if you have a 0 at the origin like this, right? whatever frequency you are sending through the block, every signal, right, whatever the frequency may be, will undergo 90-degree phase addition. This is positive phase. And if you look at the magnitude in dB, here you can see dB. 0 dB means unity. That is no attenuation, no amplification. If you send peak amplitude, whatever voltage of your signal, response is also having the same magnitude, right? Amplitude will not change. For what? 1 radians per second, somewhere here. But after that, when you have different frequencies, when you increase, the magnitude also increases like that. So from this graph, you can figure out any frequency in this range, 1 to 10, any frequency. You can calculate what is your phase, what is your gain. If you send different frequencies, what sort of amplitude change is happening and what sort of phase delay is happening. And if you look at a pole at the origin, these are the graphs. If you have a pole at the origin, if you send a frequency signal through it, it will undergo minus 90-degree phase change. Minus 90-degree phase change. And magnitude, again, you start with 0, that is no amplification, no attenuation. But it will gradually start attenuating the signal like that. So magnitude drops, minus dB 15 over here. So you can see the 0 amplifies the signal, pole attenuates the signal, okay? So this is the effect of a pole or 0 at the origin. Now let's take our second elementary block, that is the first order block, right? Again, the first order block, if it is in the numerator, it's a 0. If it is in the denominator, it's a pole. So you can draw the block either like this or this way. So this is first order block where you have 1, 0, right? At minus Z. This is where you have one pole at minus P. So let's calculate the gain for any given frequency omega. Right? This is the block. You substitute S equals j omega. So it becomes j omega plus A. A is actually the value of the 0. Okay. So the block is j omega plus A. And you have to calculate the magnitude. And it should be plus or minus 1, because if it is 0, it is plus. If it is a pole, it is minus. So using the same gain, you represent both 0 and a pole. When you convert this into dB representation, now you know that you have to calculate log of this one. Log of this one, as you know, the magnitude of this complex number is real part square plus imaginary part square, right? And get the square root. So you have a square plus omega square, right? When you say take magnitude, real part and imaginary part, you add them together and get the magnitude, right? So square root of omega square plus a square is the actual absolute magnitude, but you take the log of it and multiply by 20. and you say dB, decibel. Now, what about the phase? Phase is tan inverse imaginary part over real part. So imaginary part is omega, it is j omega vertical axis over A, the real part, and you take inverse tangent. Now, to understand this a bit further, we can set a value for A. We can set a value for A and then simulate it in MATLAB and see for ourselves, right? If you set a particular value A and then you send the whatever frequency from left hand side, you will understand what is the phase change, what is the gain change. Okay. Now, this simple A, the pole O0, right? The location of the pole O0, and then if you send a frequency signal, right, the amount of amplitude that you get or amount of phase delay you get very much depends on A, that is the pole O0. So if you look at the total gain for milestone frequencies, which are zero frequency, right? 0 radians per second DC level. And when the frequency is equal to A, that is the value of the pole O0, we can get some insight into what is happening. So let's substitute for omega, that is the frequency signal, right? 0. So then it becomes 0 square plus A square, square root, this one, magnitude, and you take the log of that and you multiply by 20 and you say dV. Now, this is equal to log A, because A square root is A. So it is log A times 20 decibel. So this is 0 radians per second signal which enters to the plant, first order pole O0. This is the amount of gain, right? It can be amplification, it can be attenuation. Now, if you change your frequency to omega equals A, right? This is the DC level. This is some frequency which is equal to the value of the pole O0. You can write down this equation. Now, this time it becomes plus or minus 20 log square root A square plus A square. That is 2A square. That is 2A square. So you can take this 2 to the square times A to the square, right? Separately. So when you have 2 to the square root is, right, root 2. And on the other hand, A square, right, becomes A. All right. So you break this into two terms, right? 2 and A square, and take square root with 2 over here, square root with A square over here. So it becomes 20 log A plus 20 log root 2. Okay. Now, if you have a calculator, you can check this out. Check the log of root 2. It's about 0.15. And when you multiply it with 20, it becomes 3. This is the famous 3 dB thing that most of you may have heard of it. The other part is 20 log A dB. So there you can see the value of the pole O0 determines the total gain, okay, at that particular frequency. Now, if you compare this magnitude, this gain, with the gain at 0 frequency, right, when you have a 0 frequency signal, the magnitude is 20 log A dB. Now it is 20 log A dB plus or minus 3 dB. So when you increase your frequency from 0 to A is the value of the pole O0, right? The gain will change by 3 dB, for a first order block. So now we want to simulate this one in MATLAB so that we write a little code. So I want you to actually practice all of these codes. Now I have shown you many codes now, right? You better write those codes yourself using MATLAB and understand what you see, right? So here also, first order block, we partition our screen into 2 columns, right? The first column is this 1 to 1. We define our transfer function. Now this time it is 110, which means s plus 10 over 0, 1. 0, 1 means 1. Okay. So there's a request in the chat box. I don't have MATLAB. You need to have MATLAB. You need to find out MATLAB. Okay. You can't say I don't have MATLAB. When you do control systems in undergrad, in postgrad, you need to find that out. I don't want to tell how. Talk to your friends, find it out, talk to Damit, install it. If you don't know MATLAB, you can't do this course. Simple as that. Okay. So there are a lot of things that you have to do when you engage in a serious course, right? Nobody's going to spoon feed you things. You need to take responsibility. You need to do your homework. You need to brush up your whatever uh, uh, subjects that you don't have at that moment, right? Figure that out. Do additional reading. Do additional web surfing. Look at those other materials, supporting materials to get going, right? So this is a bit of a surprise to me, right? You need to find it out and install. And now we are in the middle of the course. If you haven't put your hands on MATLAB, that's pretty bad. That's pretty bad. This is something I told on the first day of the lecture, some 7 weeks ago. You need to learn MATLAB yourself. Okay, this comes with a total surprise to me. Okay, you have to do this immediately. This is now your first priority. You don't have MATLAB means you know nothing about MATLAB. That is pretty bad. That is pretty bad, right? In your undergrad course, also, if you haven't done any MATLAB, you are in a pretty bad shape for this course. But the good thing is that you still have time to recover. But it doesn't happen naturally. You need to spend a lot of time on it, installing and going through some tutorials, right? The rest few weeks will be very tough for you to get grip on MATLAB, right? And write down all these codes and catch up. So otherwise you will be in trouble, right? In the exam also, right? It is MATLAB based. I'm giving some MATLAB codes. You are supposed to write MATLAB codes, and you're supposed to have your MATLAB, your power. There's no warranty or guarantee about providing power for you. When you go to the exam, you need to make sure your computer is fully charged and can run for at least an hour or two, right? You have to prepare for that. That is a requirement of this course. Okay, it's not just simply solving problem kind of course. You are supposed to do some designs. You are supposed to simulate it in MATLAB and get some results. Right, immediately do that. Okay, so we are not providing MATLAB because it's out there. You can find it out yourself. Okay, right. So 0 at the so this is the heading is not correct. For a 0 at origin, for a pole at origin, these are actually coming from the the labels that were there, right? So now we are not talking about 0 at origin or 0 a pole at origin. This is a first order block. Okay, so therefore this green text, don't worry about that. Okay, that's not correct. But the line here is correct. Transfer function 110 means s plus 10 in the numerator, and the denominator 0, 1 means 1. So this is a 0 at 10. 0 at 10. So if I draw, uh, uh, the plane, right, like this, this 110 means, right, you have a 0 at minus 10, right? Now this is your point s equals j omega. All right, you change this s from 0 to infinity like that. Okay, when you do that, what is the gain and change and the phase because of this 0? Because of the 0. That is what we are going to figure out. So we declare the transfer function 110, 0, 1 and use the bode command. Bode sys, put the grid on. These lines are the grids, right? It's very important. And we plot it here, subplot 1 to 1. And we do the same for a first order block, this time for a pole, right? 0, 1 in the numerator means 1. 110 means the denominator, that is a pole at minus 10. So next time, it's not a pole 0, it's a pole, okay? Right. So this is the result. So what do you see? What do you see? You will see 20 dB magnitude. You will see 20 dB magnitude for low frequencies, right? And then stay most of the part of the lower frequencies, and then gradually raise up. And when you include omega equals 10, omega equals 10, which is equal to this one, right? You have 3 dB gain, additional 3 dB. So altogether 20 plus 3 is 23 dB. And after that, so as you increase frequency, right, as you go like that, you get higher and higher and higher gains. Okay. So if you give a 0 frequency, you get 20 dB gain. If you give 10 radians per second input signal, you get 23 dB gain, right? And if you increase to 10 to the power 3, right, that is about 1000 radians per second, you over here, you have 60 dB gain. So this 0 actually amplifies the signal, right? It amplifies the signal. For higher frequencies, high amplification. And at the same time, what does it do for the gain phase rather, right? It starts with 0 phase, so which means input and the response have 0 phase difference. What does it mean? It means if the input is like this, right, output is also like this. In phase, there is no phase difference. There's no phase lag. Okay. But as you increase your frequency, right? As you increase your frequency, you get here 10 to the 0. This is 1 radians per second. And you see now there's a phase, a lead, positive phase, right? And when it is over here, 45-degree phase lead. And for higher frequencies, it again levels off to 90 degrees, right? From this 0 phase difference, eventually it goes to 90 plus 90 uh, phase change. So 90 phase change means what? Oops. Right. So if this is the input for 0 phase change, this is one in phase. No, there's no phase difference, right? But 90-degree phase difference means now you know this is initial point. This is 90 degrees. This is 180. Somewhere here, right? This is 270. This is 360, right? Like that, no? So this is 90 degree. One strip is 90 degrees. So this waveform response will move forward to the left by one strip. Okay, so this happens for higher frequencies. This happens for higher frequencies. That is what is done by first order block in the numerator. That is a 0 at 10. Now, one very interesting point here is that if you look at 10 radians per second waveform, right? 10 to the 1 is 10. This is the 10 radians per second. For that particular frequency, you have 45-degree phase lead. 45-degree phase lead. And for that one, gain is 23 dB. So this phase and gain, right, for various frequencies, okay, change, but it change with some relation to the pole O0. It's some relation to the pole O0. Now, on the right hand side, you can see the Bode plot for a single pole at -10. Single pole at -10. So if you send very low frequencies, right, you will see -20 gain. -20 dB means weak. It's seriously attenuated. And when you increase the frequency, it will further attenuate like that. And when you have exactly 10 radians per second signal, you will have -20 minus another 3, right, dB. That is -23 dB gain. If you have exactly 10 radians per second signal. And at that frequency, the phase is exactly minus 45 degrees. For low frequencies, there's no phase difference, and for high frequencies, it will be minus 90-degree phase difference. So this response going back and forth, going to your left hand side means positive phase, going to the right hand side means negative phase. Okay, so you can see a 0 gives positive phase, a pole gives you negative phase. So it's interesting to understand how these individual blocks, pole or 0 at some point, right, real pole or real 0, right, affect the phase and gain of a sinusoidal frequency, which is trying to move through the block. So when it moves through the block will introduce magnitude change and phase change. Okay, so we are taking here some specific blocks, the real 0, real pole, and things like that. And next time we will take immediately after this conjugate pair, right? Then we will look at that also. Right. The second order block. So shall we take a little break, right? About 10 minutes, right? Let's take a little break now. Okay, finally, we have a second order block. It can be a second order block in the numerator or in the denominator. Okay, if it is in the numerator, it's a pair of conjugate zeros. If it's in the denominator, it's a pair of poles. Okay, conjugate pair. If it is not a conjugate pair, that is say two real poles or two real zeros, that has already been discussed in the previous section, right? So this is how we write a pair of conjugate zeros, right? And this is how we write conjugate pair of poles. Now these are all complex expressions, right? With the numerator, denominator. You know how to write gain, right? Gain is the real part square plus imaginary part square root. Or else before that, you can take this expression, the whole thing, and put this magnitude bars and raise it to the power of plus or minus 1. If it is this one, it is plus 1 here. If it is this one, it is minus 1, right? So with one single expression, you represent the gain of either of these, okay, cases, pair of zeros or pair of poles. Now, S is the variable. You substitute S equals j omega, right? Then this becomes omega square minus, and also this becomes j omega, right? So it is the imaginary part now. These two are real part. So you can clearly see the real part and the imaginary part. Now you want to take the squares, add them together and get the square root. Everything is, I think, pretty obvious here. And after that, if you want to represent gain in terms of dB, you have to take the log of this expression and multiply by 20. Again, this plus or minus comes over here. Plus if it is zeros, minus if it is poles. Okay, fine. What about the phase? Phase is imaginary part over real part, tan inverse. You know that, right? You can see imaginary part over real part, tan inverse. when you actually do this calculation, it is better when you use MATLAB, use the two argument arctangent function, that is a tan 2 function, where you can substitute real and imaginary parts separately, not as a ratio here. This is how you write mathematically. If you just divide this one, you will forget, you will lose with the quadrant information, whether this is in the first quadrant, second, third, or fourth. So that is why the arctan2 function, a tan2 function is there with two arguments, numerator, denominator separately, so that MATLAB can figure out the quadrant. Okay. Right. Again, we can dig down a bit more to figure out some additional information here. For example, if you send a zero frequency, 0 radians per second signal through this block, pair of zeros or pair of poles, what will happen to the gain and phase? So we take the gain equation and substitute 0 for omega. So then it becomes like this, isn't it? So go back and check it out. So this is the gain, right, in dB. So omega equals omega equals 0 in this case. So basically omega n square, right? So omega n to the power 4. This is for 0 radians per second signal passing through this block, right? Pair of zeros or pair of poles. So it is basically omega n to the power 4. After the square root operation, it becomes omega n to the power 2. And that power 2 comes in front, making this 20 to 40. So it is 40 log omega n dB. And second, if you substitute omega equals omega n, right? Now you have natural undamped frequency omega n. And if you send the same frequency signal, what will happen? Now the block has natural undamped frequency, and you are sending the same frequency as a signal. Okay. Okay. So when you have omega equals omega n, you can see it over here. This becomes 0 when omega equals omega n. And this one would be 2 zeta omega n square. So something like this. So this square root will go away with this square. So it is basically 2 zeta omega n square over here. So now you can break this down into two pieces, omega n square and 2 zeta separately. So omega n square becomes the first term here, that is log of omega n, and this 20 becomes 40 because of the square. And the second part, 20 log 2 zeta dB. So when you separate this into the two blocks here, right? Two blocks here, you can see the first part rather, 40 log omega n dB is the gain that you got for 0 frequency signal, the gain for a 0 radians per second signal. You can see the same gain here when omega equals to omega n, but in addition, there is this additional 20 log 2 zeta dB. So this is the additional amount when omega equals omega n. When you excite a block, exactly the same frequency, that is the natural undamped frequency of the block, you get this additional gain. Right. So to simulate this block, right, pair of conjugate poles or zeros, we write the code again in MATLAB. So let us arbitrarily take some value for theta. Theta equals 0.1 and natural undamped frequency 10 radians per second. And we write subplot 1 to 1. We separate the display into two parts, left and right. This is the left part. The system is this transfer function. What is that? 1, 2 zeta omega n square. So this is the numerator, right? And the denominator is just 1. Okay. You can write this 1 as 0, 0, 1. That is also okay because this is the second order block, right? Or if you just simply say 1, that is also okay. Then Bode-assist means you draw the body plot of the system and put the grid on, and then you have to hold the display on without actually erasing it, because you are going to put another one side by side. The right hand side of the display would be like 1 to 2. Then the system is like 1 over the second order block. Now this is two poles, conjugate pair, right? Bode-assist, grid on, hold on. So this is what you get. On the left hand side, this is the magnitude and phase plot for a pair of zeros. On the right, this is the magnitude and phase for a pair of poles, right? You saw this 40, remember 40 dB thing. Earlier, for a first order case, you saw 20 dB. Okay, now this time 40 dB because two poles. The single pole like 20 dB, two poles like 40 dB. So remember these relationships, right? So you start off with 40 dB magnitude, right? And then there's a temporary drop of magnitude when you increase your frequency to omega n, which is 10 radians per second here, and your gain drops down to 26.3 dB, right, from initial 40, but it is only temporary resonance kind of thing, and then after that increase again. And if you look at the phase, you can see right at 10 radians per second, if you send the same signal, same frequency through the block, right, you get 90-degree phase lead here, right? Whereas earlier, remember, it was 45, now this is 90. And there's absolutely no phase initially, same as before. Eventually, the total phase is 180 degrees. 180-degree phase change means one half of the cycle. One half of the cycle. So therefore, when you have the input going up, you can see the response going down. The response starts the second half of the waveform, right? So exact upside down waveform, right? But this happens when frequency is very, very large, like 100 radians per second, okay? But again, this transition is not linear, it is highly non-linear. And here you can see when you change your frequency from, let's say, about this is 10, this is 9, this is 8 radians per second, to about say this is 10, this is 11, 10.5 or something, right? Somewhere over here. This huge phase change happens. Like for example, how much should this be? I guess maybe 15 degrees to about, how much would that be? Like 170 degrees. So see this huge phase change from 15 to about 170 degrees within a matter of few radians per second. Okay, highly nonlinear transition. And all the higher frequencies pretty much same phase, and all the lower frequencies pretty much the same phase without much change. Uh, And if you look at the pair of poles, you started negative gain 40, 40 negative this time, right? It will stay at the same level for some time, and then when you reach 10 radians per second, which is the natural undamped frequency of the plant, of the block, you get sudden amplitude, right, of the magnitude. So that is about 26.2 negative, and then drops. And for the phase, it is from 0 and to minus 90, and then eventually to 180 degrees. Now, this is how the magnitude and phase changes, right? When a signal passes through a block, first order block, second order block, a pole at 0, 0 at 0, right? Now you have already completed the basic elements, right? So now you can combine these elements, right? First order blocks, pair of conjugate pairs, combine blocks, right? And use MATLAB and simulate. Use the TF command, use the body command, and plot them on screen. So I'm not going to dictate you, give you assignments like in O-level, grade 8, like that, right? Is open. Everything is open, right? For you to throw at different blocks into MATLAB and check what is the gain, what is the phase, and all, right? So it's basically learning by self, okay? So I'm only guiding you methodically to do certain things. So if you follow these instructions and spend a lot of time, usually, as you know, teaching time and self-learning time, the ratio is probably 1 to 10. 1 to 10. If you listen to me, say 1 hour, you have to work on that 10 hours, right? Higher the better. So that is how it works when it comes to advanced engineering stuff, technical stuff, okay? Especially when you develop professional skill rather than just a degree or something, right? Exam certificate. This is pretty much hands-on stuff out there. So therefore, a lot of simulation stuff, coding stuff, you can do yourself. Eventually, maybe you would agree with me saying that whoever teaches you, eventually, it's you who learn. It's you who learn. That is why some people learn self. They don't need much of instructions, guidelines. They don't need teachers, many, right? Maybe needing only to guide you in certain directions, but they learn themselves. So we want uh, you to develop that skill, because some of the things that we teach you, there's no way we can teach you the whole thing. It's so huge, so deep, so wide, right? We can only guide you, right, and to do this way, that way, and so on. It's all up to you to, to self-study. It's very easy these days, because not like all those days, you have the internet within your within reach, within your fingertips, right? You can have access to almost anything. So therefore, self-learning is very, very easy. But when you do self-learning, you have to always cross-check it with your supervisors, your teachers, lecturers, right? So that you know you are doing the right thing. Right. So therefore, please use those codes and test it yourself in MATLAB. Okay. Now I'm going to open a new discussion: phase margin and gain margin. Right. You may have heard this uh, previously, right? So rather than giving you the definition, right, I want to do this example with you, right? Those of you who are having MATLAB, right, you can start writing this code immediately, few lines, and you will see on screen what I'm going to tell you. So from now on, at least, I want you to have your MATLAB ready on your computers, right, while you are listening to the lecture. make sure you have MATLAB open and you can quickly write down these codes, and then you will stay with me, right, very closely. It will be a very nice learning curve for you, learning experience for you. As you hear to me, right, you always code the same thing on your MATLAB, and you see the same result that I'm showing you, right? So I have a block here, right? You can call it a block or a transfer function. It's an open loop transfer function for which we want to close the loop and design a controller, let's say, right? So this is a complicated transfer function, right? S plus 5, S plus 6, two zeros there. And look at the denominator. It's a third order polynomial and a second order polynomial. So there are 5 poles here, 5 poles. Okay. So you can take this and draw the root locus if you want, right? You know how to do that. Few lines in MATLAB. In about a couple of minutes, you get the root locus. And you can do all sorts of other things, whether the system is stable, what are the gains, right? All those things. Now, today our discussion is the frequency analysis of this block. If we send different frequencies to this block, what is coming out, right? Whether you get attenuated signal, amplified signal, phase delayed signal, phase lead signal, whatever, right? And we basically want to know the magnitude versus frequency and the magnitude versus phase. Sorry, the phase versus frequency. So our x-axis is frequency from very, very low frequency to very, very high frequency. And the vertical axis, one hand the magnitude, the other one is phase. So we want to look at what this block really is, right? How it responds to different frequencies. So what we do is we open MATLAB and write this numerator. Our numerator is this one. It's a convolution between 1, 5 and 1, 6. So this is how we write it. One shot, we have it. Then the denominator, using the same convolution function, 1, 14, 13, 2, 1, 14, 13, 2, and 1, 10, 2, 1, 10, 2. There you are. And we create the system using TF command, transfer function, numerator or denominator. So we have the whole block. Then you draw the Bode plots. This time is bit different. It's bit different, right? I use this command Bode sys, which means this transfer function, comma 5. And on the left hand side, it is a square bracket inside gain and phase. So this way, you can launch this command, MATLAB command, in number of ways, right? One method is, of course, this one. You just simply write Bode sys. Then you simply draw Bode plot like this. But if you launch it like this, not a single argument, but two arguments with a number here, which means you ask to draw Bode plots and also to calculate gain and phase at 5 radians per second. At 5 radians per second. Okay. So in addition to now actually this command will calculate the gain and the phase, right, for a 5 radians per second signal. If you have a 5 radians per second signal coming in to this block, what is coming out of the block? How different the signal which is coming out of the block in terms of phase and gain, right? You can calculate it using this command. And after that, you draw the Bode plot and you put the grid on. So when you do that, this is what you get. So those of you who are having MATLAB, who have coded this one, right, would now be seeing the same graph on their screens. Right, you can see for low frequencies like 10 to the minus 3, 0.001 radians per second, very, very low frequency, right? You have some gain here above 0. 0 means unity, right? 1, which means there's no attenuation or amplification. Okay, gain is 1, but now it's not 1, it's slightly above 1, so there's a net amplification of the signal, right, for some frequencies. And then around about this frequency, that is less than 1 actually, this is 0.1 radians per second, 0.2, 0.3, somewhere like 0.3 radians per second, gain reduces and it continues. After that, as you increase the frequency, the magnitude drops. Okay, eventually you will not get anything out of the block for higher frequencies like 10 to the 3, that is 1000 radians per second. The signal is very, very weak. The entire signal energy is actually absorbed by the block itself. Then if you look at the phase, for very low frequencies, there's no phase delay. The input signal as well as the output or the response, you have the same phase pretty much. But when you increase the frequency, you will see phase is going like this. And 90-degree minus, that is phase lag, is here for slightly more than 0.1 radians per second, and it goes like that. So you can do this for any block, right? Irrespective of whether it's a complicated block or a simple block. And in MATLAB, you can calculate the gain and phase for 5 radians per second. And if I go to the plot 5 radians per second, this is 10 to the 1, 10 to the 1, right? This is 10 to the 0. This is 1 radians per second. This is 2 radians per second, 3, 4, 5. This is 5 radians per second. This is 5 radians per second. So at this frequency, what is the gain? Gain is this much. Okay, closer to minus 50 dB. And the phase is like between 180 and 270, somewhere here, right? These numbers will be printed on screen when you run this code, gain and phase. Okay. Now our major discussion here is this. Now you can see that when you send a sinusoidal waveform to this block, right? Like for example, this particular frequency. What is this frequency? Can somebody tell me? What is this frequency? Where I have placed the laser pointer. What is the frequency? Can somebody answer my question, please?
It's between 0.5 and 0.6.
Yeah, between 0.5 and 0.6. Okay, fine. So what is the speciality of that frequency? This is a very special frequency. Say it again.
180-degree phase shift.
Okay. That particular frequency between 0.5 and 0.6 radians per second, right? There is 180-degree phase shift. 180-degree phase shift. So what is 180-degree? Again, I can draw it like this. This is the input, right? 180 degrees somewhere here, this point, right? This point. So the output, right, is actually like this. Can you see the exact opposite or flipping over? Now what you are trying to do is you are trying to take the feedback. You take this one and feed it back over here, right? So how bad of an idea is this? Feeding back a completely upside down sinusoidal signal. It's a bad idea, right? It's a bad idea. Because now what you're supposed to do in feedback is in fact negative feedback. You want to subtract this signal from this signal. That is what is called negative feedback. You see in the negative in the block, you see the block, right? So this is the summing block and this is the reference signal, right? And this is the feedback signal. So this is positive and this is supposed to be negative. Now when you are feeding back a signal which is 180 degrees out of phase, right? Are you actually doing what you are supposed to do? Plus minus? No. You are adding these two signals together. This is not actually negative feedback. This is going to be positive feedback. So that is a very, very bad thing to happen for a system. Right? So therefore, we say this. So this particular frequency, right, where the phase shift is 180 degrees, right? If you come up, you will see your gain is slightly below 0 dB. 0 dB means 1 unity gain. Now you are slightly below. You are not 1. You are not 1. So therefore, if I have drawn this line like this, right, which is same magnitude like this, is not correct. So therefore, I need to draw it with a lower magnitude, right? So this is not correct. The correct one is probably lower magnitude, like this, for example, right? Something like this. So when this signal passes through the block, this is between 0.5 and 0.6 radians per second, passes through the system, it becomes like this. It weakens, right? It drops in magnitude in addition to 180 degree out of phase. Now, when you feed this one back, even though it is a bad idea, you will be safe. Why? Every loop feedback, right? This signal gets smaller and smaller and smaller. So therefore, signal will not be amplified too much within the loop because it's a looping thing, right? It goes round and round and round. So every round it attenuates. That is a good news. That is a good news. System is safe even though the signal you are feeding back is 180 out of phase, because the gain is less than unity. The gain is less than unity. Every loop, the gain reduces. But how much? You can see it over here. This is the point where frequency is 0.5 and 0.6 radians per second, and also the point where the phase difference is 180 degrees. You're slightly below unity gain, right? You can figure out the dB from here to here in between, and that is what is called the margin, safety margin. We call it gain margin. Okay, now you can figure out the definition for gain margin. You know the meaning, right? Gain margin is the additional gain in the system, right? Uh, uh, for a frequency which shows 180 degree out of phase, right, in the body plot. So if you are a practicing engineer, right, you need to know what is your gain margin in the plant you are working, right? And make sure you at least to leave for let's say in terms of absolute gain, right, maybe at least about 10 or at least 5, right, additional factor, so that every loop, right, you have probably about 0.2 gain, so that it will quickly die out without causing any problems, right? But if your margin is very, very small, right, that's not good. Yeah, even though you are safe, the margin is not that wide, right? If you do any additional change in the plant, probably you will lose this gain margin and you will become unstable, right? So that is the gain margin. So let's look at phase margin. Phase margin. Now we know that our gain curve, we start over here for various frequencies, right? When you increase the frequency, gain drops to exactly 1 over here. Our gain is 1. The frequency for that is probably 0.2, 3, 4, and 5. 0.4 and 5 radians per second. And somewhere there, you see the same gain, right? Which means if you have this one, you have the same amplitude here, right? But phase is different. If you come down from here, you will see the phase at that point. The phase at that point. It is not 180 degrees, but you are close to being 180. Okay. So we can safely say that if for that particular frequency, which is 0.4 and 5 radians per second, if there is this additional phase lag, and this is the additional phase lag, if you introduce this additional phase lag, this point comes over here, exactly 180 degrees. Then you are feeding back same signal with the same magnitude, but 180 degree out of phase, right, to the reference signal. So this feedback is nasty. It is the same magnitude signal, 180 degree out of phase. You are actually doing positive feedback, where you actually supposed to do negative feedback. So the deadly condition here is that you have unity magnitude, that is 0 dB, and 180 out of phase at the same time. This is the nasty condition, right? If you have unity gain and 180 degree out of phase for a particular frequency, that is the nasty combination. So if one of them is off. Let's say gain is 1, but phase is not 180 degree. There is a margin, and that is what is called the phase margin. Or the other way, if the phase is 180 degrees, but gain is not unity, right? It's smaller, then that is the gain margin you have in the plant. So this gain margin and phase margin gives you some insight into the plant, okay, where you are qualitatively, right, where you are with respect to the plant. You need to use gain margin and phase margin, right? Keep additional phase margin and gain margin in your plant. Getting too close, having narrow gain margin and narrow phase margin, it's not good. It's not good. Right. So, do you understand everything what we discussed up to now? Are there any questions, please? No questions? Okay. So, let us continue with this one. This is also very interactive content. I want you to do this with me, right? Servo controller design. So when I say servo controller, I'm referring to very fast changing mechatronic systems like robots and other various types of fast moving apparatus in manufacturing industry, right? Where you're supposed to change your reference signal very quickly, and you want the motion control system to follow that reference as fast as possible and as accurate as possible. So when it comes to designing servo controllers, right, there are a few things we need to look at. One is the open loop bandwidth. Okay, what is the bandwidth we have? When you have a higher bandwidth, which means the speed, okay, you can command the system with fast changing references, right, and still the system can follow it. So that is open loop bandwidth. Can you adjust your bandwidth? So I am giving you a plant and I ask you to adjust the bandwidth to whatever frequency. This is a need in industry. One of the duties of a control system engineer is to adjust, modify the bandwidth of the plant. Second, phase margin at bandwidth frequency. Sometimes you are asked to increase your phase margin and maintain 45 degrees, 50 degrees, 35 degrees. Then you are supposed to do that. And finally, steady state error. you are asked to maintain a certain steady state error. How do we do that? So let's look at that using an example. So here I give you this example. I take it down. 3 times s plus 3 over s plus 4 times s square plus 3s plus 20. So it's a transfer function with single 0 and 3 poles. So I want you to design a control system for the plant to have 20 radians per second bandwidth. Okay, the system needs to have 20 radians per second bandwidth and phase margin of 45 degrees. Also, steady state error of 0.01 for unit step input. So these are the requirements, right? So I'll give you 5 minutes to get a head start. Okay, look at the transfer function, write a little code or manually calculate the bandwidth and check whether it is required value 20 radians per second. If not, how to increase that. And once you increase bandwidth, draw it again and compare it with the existing one. Right? Can you do up to that point to get a head start? Okay, I'll give you about say 5 to 10 minutes. Okay. So if you have been able to get a head start, right, you can check your results with what I'm going to show you right now. The first thing we need to do is to check, okay, what is the bandwidth of the plant right now? What is the bandwidth of the plant right now? So this is the open loop block, right? What is the bandwidth of this one without doing any modification, right? We are going to modify the plant, but without doing that, what is the existing bandwidth, right? So how do you do that? The definition of bandwidth is, right, at what point it is going to have unity bandwidth. So we are assuming that it has more than one magnitude initially, right? For not initially, but for low frequencies. But as you increase the frequency, the gain drops, magnitude drops. And at what point the magnitude drops to unity or 0 dB? Okay, so you can safely say that is the bandwidth. Sometimes when you define bandwidth in filters and all, you know it is defined at 3 dB cutoff. Okay, half power. So that is one way of defining the bandwidth. But here in control systems, you can reasonably take it as 0 dB or unity bandwidth. Okay, right. So to do that, so I want to show you how you can do everything in MATLAB like this. You first define your block in MATLAB. How you do that? You first get the numerator of the plant, that is numerator G, num G, 3 times s plus 3. 3 times s plus 3. So this is how you define it. Your numerator and your denominator is convolution of these two, 1, 4, 1, 3, 20, right? And you synthesize your transfer function using TF command, a 2-argument TF command, numerator and denominator. So that is G, right? Existing plant. Then you draw body, right? Magnitude and phase to visualize what it is and put the grid on. And also, if you want to calculate your gain at 20 radians per second, this is how you run your body command. Body command, now it is with the 2 arguments. G is the plant, this one, and after comma 20, that is 20 radians per second. So at 20 radians per second, which is the required bandwidth for the plant, right? What is the gain and phase? MATLAB will calculate it for you. So when you do that, this is the result. So this is the result. You can see the magnitude starting from minus 20. It's not unity. This is the unity magnitude, 0 dB. But you have minus 20. And there's a little uphill here, but not much. Again, roll off. And this is the phase. You have in phase, 0 degree phase difference. And somewhere here, drop sharply and eventually goes to 180 degree. It doesn't, it never goes to 180 exactly, but it reaches 180 degrees. So at 20 radians per second, this is 20 radians per second, right? This is 10 to the 1, that is 10, right? And this is 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, so for 20, it is this point, and you can see the magnitude is minus 42.2 dB. That is not 1 or 0 dB, right? It is far below that. And if you look at the phase, it is 168 degrees. 168 degrees. So you can calculate these two values. That is the exercise I gave you just a while ago to calculate the gain, for example, this one, right? Substitute S equals J omega, right? Pure frequency. Now this time it is J 20 radians per second. Calculate your gain, calculate your phase. You can do that manually, right? And these are the numbers you're going to get. Now, where are we with respect to what we are supposed to do? What is supposed to do is to have 20 radians per second bandwidth and 45 degree phase margin. So let's leave phase margin aside for a while and just try to see how we can achieve this bandwidth requirement, 20 radians per second. So now what you have at 20 radians per second is 42.2 negative magnitude. This is not enough. This is not enough. So can somebody suggest a method to have this bandwidth 20 radians per second? How can we do that? Any ideas? You can unmute your mics and answer the question.
The bandwidth adjustments for the unity.
Okay, bandwidth adjustment to unity. Exactly, that is what we want to do. But do you have any suggestion as to how we could do that?
Introduce forward gain.
Introduce a gain. Exactly, that's the point. Introduce a gain. Can you further elaborate how to calculate that gain? So now all good. We need to improve the bandwidth using a gain. Now the next step is, how can I calculate this gain? Okay, so let me show this to you. As you rightly said, we are going to introduce a gain. Okay, and this is the existing plant. This is the frequency, omega equals 20. So at omega equals 20 radians per second, okay, the plant together with the new gain, right, the total gain of the plant should be equal to 1. So this is not dB, this is absolute magnitude, okay, so it should be 1. So this is the plant, S plus 3 over S plus 4, whatever, right? This block, this one. So remember, for the transfer function, if you introduce any value for S, say pure frequency, right? It becomes a rational polynomial of S, right? So when you substitute S equals j omega, for example, it's a complex function. You can calculate the gain and phase. So that is the gain and phase of the block, right, for that particular frequency. So you can manually do that. This is not control systems. It's complex number theory. So this is that block evaluated for magnitude when when omega equals 20 radians per second. Okay. So the answer is 129.3. You need an additional gain of 129.3. Because you saw here, your gain is very small, minus 42.2, very small gain. You need to have additional gain to improve this. And this additional gain is 129.3. So this gain can be calculated in MATLAB very easily. Now this is a gain of the plant for 20 radians per second, actual gain. This is the phase of the plant for 20 radians per second. So gain G and phase G, they are equal to the absolute value of this minus 42.2 dB and 168 negative degrees respectively. So these two numbers, okay. You have to watch out the gain. Gain can be represented two ways, absolute and dB, right? So in MATLAB plot, it is dB, right? But in this calculation, it is in absolute form. So therefore, all what you need to do is to get the reciprocal of the gain, that is 1 over gain G, and equal it to the forward gain. And you modify your plant with this new gain K. So it is K times G now. So we'll give it a new name like G1. So we keep developing or modifying the plant. Initially it was just G, now it is G1 with this new gain, right? So then you can draw the new plant using this command Bode G1. So when you do that, this is the result. Okay, so this black line here, magnitude curve, is what was there initially, and this green one here is parallel to the black one but elevated by the additional gain K. Is a constant gain. So therefore all the frequencies will have additional gain because of that. Is frequency independent gain for all the frequencies. So that is why this green line is parallel to the black line. And now you can see at 20 radians per second, if you see where the magnitude curve intersect the 0 dB line is exactly at 20 radians per second. So you have achieved the bandwidth adjustment this way. So bandwidth adjustment is as easy as this. You need to calculate what is the gain at that particular required bandwidth frequency and get the reciprocal of that and use that as an additional gain in front of the block. So when you do that, you will have exactly the same bandwidth, which means at that bandwidth frequency, the gain will be unity or 0 dB. Right, now you have adjusted the bandwidth. Now you can think about the second criterion, that is what? Phase margin to be equal to 45 degrees. So can we now pay attention to that? 45-degree phase margin. So how do we calculate phase margin? Can somebody explain that using this illustration? What is the existing phase margin? How can you read it?
Minus 168 degree.
Minus 168. Is that the phase margin? Now this phase margin discussion, phase margin, gain margin,
Minus 55 degrees, sir.
say it again.
55 degrees.
55. How did you calculate 55?
45 degrees.
45. So where did you get that from?
This, where this 20 minus 20 starting to drop. That is nearly frequency. 800. So 600.
Go on. Give me the complete answer.
And at the 600 degree, 600 radians per second.
600? Where is 600?
Sorry, 60.
Give it a try. Yes, that's okay.
60 radians per second. The phase angle is nearly 135.
60
So the difference
radians per second. 60. So 60 is this is 100. This is 10. This is 20, 30, 40, 50, 60. This is
Sorry,
60.
sir, 6 before this.
6 radians per second. So this is 1, 2, 3, 4, 5, 6. What is the speciality of 6 radians per second? Is it a special frequency?
That is where gain is dropping below minus 20 dB.
So this is what we have right now. Now let me explain this again. Now, when a sinusoidal frequency, sinusoidal signal of a certain frequency passes through a block, if it undergoes a 180-degree phase delay, okay, and keep the unity DC gain, which means the same gain, okay, you are in a very bad situation, because the moment you feed back that signal, you are actually doing positive feedback. That is not good. Now there can be various combinations of these things. You are feeding back a 180-degree out of phase signal, but the gain is not 1, more than 1 or less than 1. So more than 1 is again disaster, right? Less than 1 can be okay, because successive loops, it will be died out, right? Now, it is a qualitative judgment. How safe you are, what is the margin available, more than being a very crisp, definite design rule. It is basically a guideline. Okay, basically a guideline. Now the two definitions are very, very definite. That is why they are called definitions, no, right? So whenever you have unity DC gain, the unity gain, that is 0 dB over here, right? You can see the 0 dB level, right? At 20 radians per second. Now you have 20 radians per second signal, let's say, going through the plant, right? It will not have any magnitude change. It will have the same magnitude, input and output. Only difference is it is phase shifted by 180 degrees. Right? So look at this one. If it happens like that, you are in a very, very bad situation. So pay attention to this green line, okay? You have unity gain or 0 dB at 20 radians per second. Now, on top of that, if you have 180 degree phase shift, this is a perfect combination for a disaster. Perfect combination for a disaster. And after that, there are other combinations for disaster. That's okay. But this is the gateway, entry point. Okay. So that you need to look at that point, what is your phase, existing phase. So for that, you come down to this one and see your phase is 168. Your phase is 168. It's not 160 or 180. So therefore, you can be happy about it. Right? The gain is 1. Gain is 1. So one condition for the disaster is already satisfied. It's already there. At 20 radians per second, gain is 1. But if you look at the phase, there's a second factor to make things unstable. Is not achieved yet, right? The phase is 168, not 180. But can you be really happy about it? I don't think so. Because 168 means you have only another, how many degrees to 180?
12 degrees.
You have only
12 degrees.
12 degrees. You have only 12 degrees, which is not enough. 12 degrees is very, very small margin. Let's say you change a little component in your plant, you do a little modification to the plant, you can lose this 12 degrees margin and all of a sudden you are unstable. These modifications, changes in the weather, changes in temperature happens and affects the machinery, so that your phase margin changes time to time, right? 5 degree, 10 degree, it can happen because of various reasons, right? And if that brings you, if it makes the perfect combination for disaster, right? That's something that you need to avoid happening. That is why you need to maintain a wider margin, 40, 45 degrees. In that case, even if the margin changes a little bit, 5, 10 degrees because of various reasons, you still have sufficient margin, right, to be stable. So what you now say is that this, look at the block you have, your transfer function, calculate the gain manually. This is when you do manually, right? You calculate the numerator gain minus the denominator gains. Substitute for S, J20, right? It's a complex number calculations now. So you have the first part here, tan inverse 20/3, second and third parts like this, total 168. This is how you manually calculate the gain, the phase for 20 radians per second. In MATLAB Bode plot, you have it already calculated. Don't have to do manually. You just need to go to that point and click it. You will see this pop-up box where these numbers are displayed. Okay, so this is alternatively, you can manually calculate 168. So the margin available right now is 12 degrees, not adequate. You need to add phase to the plant at 20 radians per second. And the additional phase you require here is the required phase margin minus what is existing, that is 33. You need to add 33 degree phase at 20 radians per second to the plant. And how can we do that? How can we add phase to the plant? How can we add phase to the plant? Can somebody answer that question, please? How can we add phase to the plant? Go ahead. I think we had this discussion some time back. The compensators, actually what we are trying to do is a compensation process, modifying the plant. If you want to add phase to the plant, any plant, you need to bring a lead compensator. Simple. Use a lead compensator to provide this additional phase to the plant. Okay, right. So let's see how we can do that. This is the phase adjustment using a lead compensator. I think you remember the lead compensator discussion we had some time back, right? Right. So a lead compensator is a block, additional block, right, that you bring in front of the plant. And this new block has a 0 and a pole, and pole is to the left of 0, right? You know that. Now we are working on the frequency response. So therefore, we are traveling through the vertical axis here from 0 to infinity. This is our j omega, various frequencies, right? Input frequencies. This is 0 frequency and high frequency. So at some point of time, when you have s equals j omega, you are here, right? You draw the line to 0 and to the pole, and you see these two angles. For various frequencies, various points here and here and here, you get these phases also different, right? So at a given point, j omega, right, the phase added by the phase lead compensate is this minus this. This is a bigger number, bigger angle. This is a small angle. This minus this. Okay. So if you write down the equation, the gain, the phase added to the plant by the lead compensator, which is phi LE, the phase of the lead compensator is this angle, that is tan inverse omega over ZLE minus this angle, tan inverse omega over PLE. And as you know, for low frequencies, for low frequencies over here, j omega, when it is over here, what is the phase added to the plant for low frequencies? Can somebody answer that question, please? For low frequencies, like when j omega is very low, very small over here, what will happen to the phase added to the plant? What is the additional phase? You can look at that diagram, triangle, and when you bring this point down here, closer to origin, what will happen to these two angles?
Nearly 0.
Both angles will approach 0, which means the difference is also 0, right? So the lead compensator will not add any phase for low frequency signals. Now we are trying to understand what this guy is, the lead compensator. Now if you look at very high frequencies, when j omega is up in the sky, you move it further up and up and up, then what will happen to these two angles?
Closer to 90, and again the difference becomes 0.
Yes, both angles will reach 90 degrees and the difference will again be 0. So now you understand the lead compensator, right, has no phase contribution added to the plant for low frequencies as well as high frequencies. So somewhere in between, right, something like this, you can have some significant phase contribution. Some significant phase contribution. So now we can safely say, if you increase the frequency from 0, gradually the lead compensator start giving you some contribution phase added to the plant. And at one frequency, it has the highest phase contribution to the plant. And after that, when you further increase the frequency, the phase contribution drops down to 0 again. So it will be like a bell-shaped curve. It will be like a bell-shaped curve, right? So with that understanding, with that intuition, now you can say that, okay, we want to add, right? We want to add how much? We want to add 33 degrees using this lead compensator, 33 degrees for 20 radians per second signal. You precisely design for that, because you know phase lead compensator increases the phase addition to the plant when you increase frequency, but only up to a certain frequency, and after that, where you get the maximum phase addition, and after that it will roll off again, reduce the phase contribution as you increase the frequency. Okay, so we want to get to that peak point, the maximum phase addition, and we want to make sure that that happens at 20 radians per second. 20 radians per second, because this phase addition is required at 20 radians per second, not anywhere else. Is that part understood? Has everybody understood that point? Ratnayaka. So Did you understand that point? Rumesh, did you understand that point? I can't hear you properly. Arya Tilaka, did you understand? Kalana Gunasinghe, did you understand that point that the lead compensator has to provide 33 degrees at 20 radians per second, and that it produces phase less than 33 degrees below and above 20 radians per second? Is that point clear to everyone? If not, tell me so that I can explain it again. Sachit Ratnayaka, is that clear to you?
Yes, sir, it is.
Okay. Veerasinghe, is that clear? Gane Gidara, is that clear to you?
Yes, sir.
Okay. Vikamarachi, is that clear to you?
Yes, sir.
All right. Gunasekara, how about you?
Sorry, sir.
Halal Deen, how about you?
Yes, sir. Understood.
Yes, okay. Then Munasinghe, how about you?
Understood, sir.
Understood. Mustafa, is that clear to you?
Yes, sir.
Okay. Nasif, is that clear to you?
Yes, sir.
Right. Palavatta, how about you?
Sir, clear, sir.
All right. Excellent. So now the problem at hand is very clearly defined, right? Actually, if you look at a complex design problem, it is actually a combination of a number of small, precise problems. Okay. So you need to break down the whole problem into different pieces, individual small blocks, and then solve one by one. So that is the way forward. Okay. There's no way to grab the whole problem at once and solve it. No, it doesn't happen. So now our task is to design this lead compensator, which gives us 33-degree maximum phase at 20 radians per second. And this is the phase equation, the lead phase lead. This is the zero of the compensator. This is the pole of the compensator, right? Omega is a variable. Phi is the phase offered by the compensator. It is also a variable. Now I want to tell you something else. For lead compensators like this, right? Because you know there's a maximum phase. This is the maximum phase lead, right? This minus this is this one. In trigonometry, you know that, right? Rather geometry. There is a particular frequency that gives you the maximum phase lead, and there's a theory proving that this particular frequency where you get the maximum lead, that is omega phi max, the frequency for which you get the maximum phase here, maximum phase lead, is given by this equation. Square root of the product of the zero and the pole. It's a very interesting and helpful equation, isn't it? If you place your zero and pole arbitrarily and you multiply them together and get the square root, and if you get to that point, you get the maximum phase, and below and above that you get a smaller angle. This is a certainty, mathematical certainty. So we can make use of that in the design, right? Because here this is not well posed, because you have both this zero and pole unknown, and phase is a dependent, omega is independent variable, right? For various omegas, what is the phase? Now all of a sudden what we do is we use this equation into that very specific moment where you fix omega to omega phi max, which is the frequency which gives you maximum phase lead, and the maximum phase lead is phi Le max or phi max. So I can replace this generic phase lead with maximum phase lead phi max, and then I need to change omega to omega phi max here and here, because whenever phi becomes phi max, omega becomes omega phi max. Okay, this is a very specific case, whereas this one is the general or generic equation. This is a specific moment where you have maximum phase lead for that particular frequency, and we want to make sure that this maximum the frequency where you get the maximum phase is actually 20 radians per second. So down the line we're gonna substitute 20 for omega phi max, and when you do that, on the left hand side the required phase is 33 degrees. So you substitute 33 here, substitute 20 here, okay, and here also. So, but still you have two unknowns, zero and pole. So for that, we want to get rid of one of them. So we use this equation for that, right? If you look at, say, for example, here, omega phi max over PLE. So look at this one, omega phi max over PLE. Get the square of both sides. Omega square phi max is equal to ZLE PLE, right? So what you have here is omega phi max over PLE. So isolate one of these omega phi max. There are two of them. Take one of them here and get this PLE to the left hand side. So then you have this expression on the left hand side. On the right hand side, it will be 0, that is ZLE over omega phi max. The remaining one comes over like this. Now this equation is single variable, right? All the other things are known. So you can calculate ZLE using a numerical technique, right? And when you do that, I can give you the answer. The answer is 10.8. The answer is 10.8. So if you know the 0, right, 10.8, and omega phi max is 20 radians per second, you can calculate your pole, right? And it will be 37. Now you have this lead compensator where the 0 is 10.8, the pole is 37, right? 10.8 and 37. You can simply draw this body plot of this one in MATLAB very easily. When you do that, you will see this one. This is the body plot of the lead compensator. What do you see? You see there the frequency axis. This is 10 to the 1, this is 10 to the 2, right? You can see the peak phase contribution at 20 radians per second and that maximum is 33 degrees. And below that, or before that, and after that, you have different phase contributions, right? Because this is not a very, very clinical thing. When you want to lift, when you want to give additional phase to a particular frequency, the remaining neighboring ones also get affected. It's like chemotherapy, right? When you treat part of the brain, the neighboring cells also get affected, right? Because it is not that clinical. Then if you look at the magnitude, it's like this. So at 20 radians per second, you have 0 dB. Look at that, 0 dB. So gain is not going to change. This is exactly what we want. Because we have already set the gain to unity, right? Because this is the bandwidth frequency. We don't want to mess up with that one. So the gain at this point is unity. And before that and after that, there are variations, but that's okay. Now you have designed the lead compensator. All what you need to do is to put it with the plant. Right. So this is how we do that. The lead compensator, right? When it comes over here, right? The magnitude of the lead compensator should be 1. So this is almost 1 here, right? Almost 1 here. Almost 1 here, but not exactly. Not exactly. So we have to perfectly adjust it. If you want to do that, this is the way. This is the lead compensator is plus 10.8, is plus 37. 0 and the pole. And this is additional gain, right? We want to introduce to make it unity so that the already adjusted bandwidth is not changed, right? So you calculate the magnitude of the 0 and the pole for 20 radians per second, and the additional gain, the total gain should be 1. So the additional gain should be 1.85. 1.85. Okay. So with this additional gain, you design your lead compensator, right? S plus 10.8, this is the 0. S plus 37, this is the pole. This is the additional gain, 1.85. To make sure the total gain is unity, right, at 20 radians per second. And this is the gain that we use to adjust the bandwidth, 20 radians per second. This is the original plan. Now you can draw the Bode plot again. This time I'm not going to show you any code. You can do it yourself. This is the new Bode plot after adding the lead compensator. So you can see it here. The green one is what you already know, right? Bandwidth adjusted plant. Now with the lead compensator, it is the red one here. You can see the red one here, right? There's a slight change with the green one, but there's absolutely no change at 20 radians per second. The bandwidth frequency is the critical frequency. There's no change there. But if you come down to the phase plot, you can see it was way down over here at 20 radians per second, 168 degrees. But now you have lifted it up. It's over here. And now the phase is 135, which means you have another 45 degrees to 180 degree level. Okay. You have maintained this 45 degree margin. This is very safe now. This is very safe now. Okay. You have lifted the phase curve up, to be precise, by 33 degrees at 20 radians per second. Okay, so we have adjusted the bandwidth, we have adjusted the phase margin also. Any questions so far? Is everything clear up to now? All right. If there are no questions, let's wind up today's session there. Right. I will continue from this point onwards next week. Right. Thank you very much. I'll see you next week.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.